All right, so today we have maybe our most important topic of the whole year coming at you. So if there's ever going to be a day where you put your phone down and really try to focus, today would be a good day, or really the next 5 or 6 days would be great. So limits is what we need to talk about. So limits is a major foundation of calculus. It's something that we're able to learn about and understand this year, and then it kind of gets taken to a new level next year. So I'm going to keep forcing these on you all year, um, and making sure that you don't forget how to find limits and what they mean. So today we got just a little bit of an introduction to a major topic here. So let's start with some notation. So the notation that you're going to see is something that looks like this. So let's talk about how to say this first of all. So if I was going to say this, I would say the limit as x approaches infinity of f of x. Okay? So that's how I would say that. The limit as x approaches infinity of f of x. Now there's all sorts of different limits that you can do. Today we're going to talk about limits at infinity. In a couple days we're going to talk about limits at a point. So you might see the limit as x approaches 2, or the limit as x approaches -7. Okay, but we're going to talk about the limit as x approaches infinity today. All right, so what is this limit thing? What is this? So if I'm talking about limits at infinity, which is what we're going to focus on today, here's really what we're talking about is, what are my outputs doing? Or maybe what are my outputs approaching? As x approaches infinity. Okay? So that's really what this is asking you to figure out. It's saying, look at this function, f of x. We'll put an equation in there in a minute. Look at this function and tell me, what are my outputs doing of this function as x gets really, really close to infinity? Okay? That's what the limits at infinity are asking us to do. Now, you guys have actually already learned this. We just called it something different before Thanksgiving. So do you guys remember what we were doing here? So before Thanksgiving, we had a different name for this. We just called it end behavior. Okay? So the end behavior of our function, really what we were doing is we were finding the limit as x approached infinity. Okay? So let's kind of flash back and let's talk about the end behavior of functions and see if we can apply this to our limits. So let's start with one that's nice and easy. So let's look at the limit as x approaches infinity of x squared. Man, this is kind of exciting. Your first limit. I feel like you guys are really growing up right in front of my eyes, except you're at home, so I can't see you. Okay, but what's going on here? So what is this question asking? This question is asking, as x gets really, really big, as x is approaching infinity, what is the output of x squared doing? So the best way to do these, in my opinion, is to try to picture what does this function look like on a graph. So x squared, so these are one of your parent functions, looks like a touchdown. Okay, so there's x squared. So as x approaches infinity, well, that would be this way. As x goes to the right, where's your y value going? He's going up forever and for always. So as x approaches infinity, y is approaching infinity, so this limit would be positive infinity. Okay? And that's really all there is to it for limits. That's limits at infinity. What's the end behavior doing there? Okay? Now notice, I could also do something like this. So let's find the limit as x approaches negative infinity of x squared. All right, so now what's this question asking? Instead of looking as x gets bigger, 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 now we want to know the limit as x approaches negative infinity. So this question is saying, as x gets really, really negative, what are my outputs doing? They're getting really, really positive. So this would be positive infinity. Okay? So the gist of our limits at infinity, today it's really not necessarily a new concept, it's just new notation for today. We really are just saying, what's happening at the ends of my graph? As x gets really, really big, what's y doing? As x gets really, really negative, what is my y doing? Okay? So I'm going to go and erase the board, and we'll look at some that maybe are a little tougher. All right, so let's take a look at this limit here. So this says the limit as x approaches infinity of x squared plus 3x plus 1 all over x cubed minus 7x plus 10. So we need to figure out what does this mean, first of all. So this is asking us, as x gets really big, as x approaches infinity, what is the output of this function doing? Okay, so let's kind of flash back to our rational functions from before Thanksgiving. So if you remember when we did end behavior on our rational functions, there were actually 3 types of rational functions that we could look at. Okay, we could look at bottom heavy. It could be top heavy, or it could be balanced. So let's just do a real brief review of our end behavior with our 3 different rational functions. So bottom heavy was the best. So if you remember, bottom heavy is when the degree on the top is smaller than the degree on the bottom. Okay, so what do we remember about our end behavior here? So if it's bottom heavy, every single time we have a horizontal asymptote at y equals 0. Okay, and remember, our horizontal asymptotes determine our end behavior. So we know anytime there's a horizontal asymptote at 0, as x gets really, 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 really big, or x gets really, really negative, our graph's flattening out at that horizontal asymptote. Okay, so if you remember, we would write like as x approaches infinity, y approaches 0. As x approaches negative infinity, y is still approaching 0. And that's true for every bottom heavy function that you will ever see. Okay? So anytime we have a bottom heavy function, your limit at infinity is going to be 0 because you have that horizontal asymptote. Alright, let's talk about top heavy. Alright, so this, that's bottom heavy. Come on, Kurt. Alright, here's top heavy. The degree on the top is 4. The degree on the bottom is 2. So how did we attack this? So if you remember, we took the terms that dominated. So that'd be x to the 4th over x squared. And we analyzed those terms. So x to the 4th over x squared, that reduced to x squared. And we said, okay, well, I know what x squared looks like. X squared is one of my parent functions. It looks like this. So the end behavior of this big, confusing rational function is going to be the same as the end behavior of this nice, easy parent function. And so we said, as x goes to infinity, y goes to infinity. And as x goes to negative infinity, this way, y is also going to infinity. Okay? And remember, just because it's top heavy doesn't mean it's always infinity, infinity. It could be top heavy and they could both be going down. It could be top heavy and one's up, one's down. So you have to look at the terms that dominate to figure out what the end behavior is going to look like. Okay? Is there a horizontal asymptote if it's top heavy? No, there's no horizontal asymptote if it's top heavy because the end behavior is not restricted by any horizontal asymptote. And then lastly, we have balanced. So this is balanced. The degree on the top and the bottom is 2. And if you remember, we would look at the leading coefficients. So that'd be 3 over 1. So that means there would be a horizontal asymptote at y equals 3. And so we would say as x approaches infinity, y approaches 3. As x approaches infinity, y is still approaching 3. Okay? So if you remember these rules, then limits at infinity are going to be very straightforward because it's really just asking about the end behavior of our functions. All right, so now let's come back to this one. So the limit as x approaches infinity of x squared plus 3x plus 1 over x cubed minus 7x plus 10. Well, is this top heavy, bottom heavy, balanced? Well, this is bottom heavy. So what does that tell me? That tells me there's horizontal asymptote at 0, which means as x gets really, really big, my graph is going to be approaching 0. So that limit is 0. All right, that's pretty easy. Let's do a couple more. Alright, let's see what we got. So, second one is x approaches infinity of 4x squared plus 8x plus 1 over 2x squared minus 8x plus 10. So the question you need to ask yourself, is this top heavy, bottom heavy, or balanced? Well, this is balanced. The degree on the top and the bottom are both 2. So what do? I'm going to look at my coefficients, which is 4 over 2, which is 2. So that means there's a horizontal asymptote at 2, which means as my graph gets really, really, really positive, my outputs are approaching 2. Okay? Now notice, I'm not saying that my graph is ever going to be equal to 2. This is just saying that's what my graph is approaching. My limit tells me what is my graph approaching as x gets really, really positive or really, really negative. All right, in the last example here, the limit as x approaches infinity of negative x cubed minus 8x plus 10 over x squared minus 7x plus 1. So again, I got to look at the terms that dominate because this is top heavy. So top heavy, so I'm looking at negative x cubed over positive x squared, which reduces to negative x. Okay, so what does negative x look like? So that's a linear function with a negative slope. So b looks something like that. So I want to know the limit as x approaches positive infinity. So as x goes this way, where's my y value going? It's going down, all the way to negative infinity. So this limit would be negative infinity. Okay? So hopefully that makes some sense for you. The key thing that you got to be careful about when you're doing these is don't get too comfortable. Let me just give you an example. So let's look at this one. So this says the limit as x approaches negative infinity of x squared minus 7x, or x squared minus 7 over x plus 2. So you just got to be careful about, are they asking you to limit at positive or negative infinity? So let's just go ahead and roll through this one while we have it. So again, this is top heavy. So I need to look at the terms that dominate. So that's x squared over x, which reduces to x. So my limit is going to behave like this linear function right there. But got to make sure that we're looking in the right direction. So the limit as x approaches negative infinity, so that's this way. So as x approaches negative infinity, my graph is going down. So this limit would be negative infinity. Okay, so just kind of keep that in mind while you're doing these limits. And then the last thing I'll say is if I gave you an equation and you don't know what it looks like, what could you do to figure out the limit as x approaches infinity? I would just graph it. Okay, so ideally we should be able to do these without a calculator, but someday maybe I'll give you some really goofy equation like, I don't know, the limit as x approaches infinity of e to the x over cosine of x, or just something that's really, really weird looking. So I don't know what that looks like, but if I grabbed a calculator, I typed it in, and then I could just kind of zoom out on my calculator and see what's going on as x approaches infinity. Is there a horizontal asymptote? Is it getting really, really big? Is it getting really, really negative? And then I could just evaluate it that way. Okay? So most of the ones that you're going to see on your homework are going to be rational functions or polynomials that you know the end behavior of. But keep in mind, you could find just about any function's limit if you graph it and know what it looks like. All right? So let me know if you need any help, and have fun doing your first round of limits.